Welcome to What Is It About the Weather? Where once a week we explore the many ways in which weather intertwines itself into our everyday lives. I'm your host, Mark Jelinek, and this week we're going to get back to where does my forecast come from? We're going to be talking about the corrections, build on the first couple episodes in the series. Now, before I get too deep in the episode, reminder, whatisitabouttheweather.com/survey. whatisitabouttheweather.com/survey. Now, I know I mentioned it last week, and I'm going to continue to mention it. I appreciate those of you who took the time to fill out the survey. Some of you did. And as with all surveys, anybody who's ever done one knows you tend to get a very small response pool. But I need to get it bigger, folks. Now, I'm employing some other podcasts in the weather podcast family to get responses as well, but I really need yours. So please take a moment. If you're not doing anything where you put yourself in danger, do it while you're listening to the podcast. It's mobile friendly enough. It's easy to take, takes about a minute. And your feedback would be very, very helpful. It's focused on my U.S. audience, but my international folks, your feedback will be helpful as well. It would be useful if you respond in one of the questions where there's an other. You just put international in there. You can put your country if you want. But all the responses are helpful in shaping our understanding, not just mine, but our understanding. And I'm going to be presenting this at a conference in January about how those of us who talk about weather-related topics in the podcast realm are reaching or not reaching our listeners. So thank you if you've already taken the survey, and if you haven't, please just take a minute and do it. All right. Now, how many of you know what squirrel is? Yeah, I know. It's a furry little creature running around the ground. And that it does this time of year, out in the northern hemisphere anyways, out collecting nuts, getting ready for winter. But it has also become synonymous with distraction, right? And you can go look up on the internet why that is and catch some cute little videos as to why that is. But I have my squirrel moment going on right now. And those that follow me on Twitter will know what that is, at least one of my primary ones, which is yesterday. The forecast became official. There was a probability of wintry precipitation in my area. And yes, we've already had a little bit of light sleet mixing in with the raindrops this morning as I had my coffee, which is always a nice thing. But this is a bit unusual for this time of year where I am. Actually, it's really unusual. I was trying to think back if I remember winter weather this early in the years that I've been in Atlanta, and I'm not sure that I do. I'm not saying it has or hasn't happened this early, but this is kind of early, and we're expecting some meaningful potential snowfall later today. That said, it's been really warm, all right? So while we may get some nice fluffy stuff on the grass and the non-roads, I don't think the roadways are going to have too much of a problem. It's supposed to get down close to freezing tonight in terms of the roadways, but it's been so warm. I don't know that we'll see major problems. And you know how no one's freaking out. This is really weird. All the schools, for the most part, not all of them, but most of them were still having regular hours today. So we'll see how that goes. Hopefully, if you follow me on Twitter, you'll get a chance to see a few pictures. I may post some if I get some nicer ones on Instagram and whatnot. So keep an eye out. Now, as always, I like to throw out some miscellaneous things. That was one of them. The other one that's really caught my attention lately is what's going on with all this CubeSat stuff. Now, for those that don't know, a CubeSat it's a little guy, right? About 10 centimeters, about 4 inches square. It's not exactly a square. I'm not going to get into all the details. You can read about them online. And you kind of stack them together. I mean, they can be, one unit is a little box, right? And you can stick a bunch of them together. But the idea is pretty simple. It's built with everyday parts that are available today. And you throw them up in an orbit. And they do what big fancy satellites have been doing for a long time. Cheaper to put up there. In other words, cheaper to replace, cheaper to renew with newer technologies. But at the same time, that means maybe it won't have the cutting edge stuff. So we're in this experimental phase. What can they really do for us? Can they really be useful in surveillance? Can they be really useful in weather monitoring, right, which is why it would be of interest to me. But I got to know why the launches with these things keep failing. Now, some of them gone up. What you tend to do is you throw a bunch of them up there. That's the idea. They can't cover quite as much area, and they're going to orbit a little closer to Earth than, and you've heard me mention different types of satellites than some of the ones we have that hold a fixed position. But the whole idea, again, is you throw a bunch of them up. It's easy to replace one if something happens to one. And they form generally what's called a constellation. Again, small in size. But different companies out there, whether it's Planet or the latest one was Spire. So, again, you can read about these different companies, and I talked about this in my class about what they're doing, and there's some really neat videos if you want to understand, and I'll put one or two in the links in the show notes. There's been some interesting stories about it, but there's been multiple failures from some pretty prominent things. One of the, here in the U.S., SpaceX is one of the big companies that's getting into the launch side of satellites and whatnot. And they haven't had a lot of failures, but one of their big failures came with a bunch of these things on board. This time it was in Russia. They're working on their new spaceport, and they've now had a couple failures with these things on board. And it makes me, this conspiracy theory comes out. Is somebody trying to sabotage all the CubeSats? No, I don't think that's really what's going on. But it is interesting how many failures we've had with these things, not to the fault of the little satellites, but to the fault of getting them launched. And it is a reminder of how dangerous still getting stuff into space is. Any case, if you're interested in that kind of stuff, take a look at the show notes. All right, let's get on to the main story. I know you don't want to listen to me babble all day. And, I'm hopeful that I'm going to be out looking at snowflakes at some point anyways. Back to, where does our forecast come from? Now, when I had originally envisioned this series, thanks to one of our listeners, Kevin, who suggested it, I could have easily come up with probably a year's worth of episodes. No, not really. But I started with about 10. How would I break things down? And I really could have done that. I think a full series of 10 would have been a lot of detail, and a lot of you probably would have been sleeping throughout the episodes. So I whittled that down to 5. And I think I've gotten it to 4, and we've done 2 of those. So we'll have one more after this one. I kind of looked at one that I said I think that it would get a little too technical, and I bunched some of it in today and some of it into the final episode. But the first one was about data. Where does the data come from that drives our weather forecast? And that one was done on October 20th, and it's episode 69. I'm kind of restating this, so if you haven't listened to them and you're just new to the podcast or you missed them for some reason, so that you can go back and listen to the precursors to this episode. And the second one was on November 10th. It was episode number 72, and there we focused on the models, what's actually happening. Once we get all the data to the computers, how does it go from there? Now we're going to be looking at the other side of things. Like I said, one episode that I'm not going to do, and I could have spent a lot of time in, just because I've spent so much personal time in it, was the outputs that come out of the models. What they're like, what their structure is, how much space do they take up, all these things. I literally could have spent a lot of time, and the more I thought about it, though, is like I could see everybody. Even the person who requested the episode, he talked to me after the first one or sent me an email. It said he enjoyed it. He could have used more detail because he's kind of a computer guy, and I got that. But as with everybody, I've got to look at everybody and say, would they stay awake? And I think even with that episode, I probably could have put him to sleep. Maybe not. Maybe he would have enjoyed it. So I really wanted to take the focus, and this one's a little tricky because it's not exactly linear from point A to point B. So I'm going to be talking about a broader process that we call, I've named the corrections. And I've named it that because your tendency might be, okay, the model spit out all this data. Okay, Mark, you're almost done, right? Maybe an episode between that stuff coming out and how I get the forecast on my phone or my television, how, different ways it's delivered. And we're going to kind of hit that in the final episode. But there's a lot more to it than that, right? Your tendency is to think, oh, that thing spits it out, it's gospel, go. But the reality is we're not even close. That is not to say that many of us, including you, might see raw data from the model put into a graphic or some sort of text-based forecast. But many of us, and most of us that get a forecast, quite often it's gone through some sort of correction. Alluded to them a little bit last time when I talked about errors and biases. So let's do a quick refresher as we go and just talk about the difference between the two. So an error, every forecast has errors, right? I don't care whether you're forecasting weather or let's say you're forecasting what a stock might do over the coming year, or even companies. Any publicly traded company, they have to do somewhat of a guess, right? It's required by law that they tell you, we think we're going to earn or lose this much money in the quarter ahead. And then they kind of revise it as they go throughout the quarter to give you a final number, and they may do it for the year ahead. Just it depends on country you're in and what the legal requirements are. But trust me, they don't like necessarily doing that and throwing that out there for the whole world to see. But they're trying to keep a company that, where their stock's being traded publicly from misleading folks, right? It's one thing if you're doing it internally or trying to understand things, but trust me, those forecasts are not easy to do for them either. And that's why they tend to give you ranges. It's not a set number. Same with weather forecasts, like we've talked about. But some of the better forecasts give you a range of things. But I don't care which of us it is that are doing that. They all have errors, folks. They all have some sort of error. Sometimes it's bigger errors. Sometimes it's smaller errors. And that's why ranges are used to try to capture what the error, the logical error could be, because it's hard to predict with certainty events in the future. Now, some of the errors you might say, let's get back to the weather component. An error today might be, let's say the temperature is 1 degree too high. Tomorrow it's 2 degrees too low. Day after that it's 3 degrees too high. Whatever it might be. But if at first glance you look at that and go, those errors seem random, right? And there are a lot of random errors in the forecast. Lots of causes, quality of data, the model itself. Maybe it's trying to resolve your forecast at a point, but it generally thinks in a big grid. Creates these errors. But there's a flip side of that, something we call bias or systematic errors. All right? And these are things when you look at it that you see a pattern. And you say, generally speaking, it always puts 1 degree too much on my high for the day, or 1 degree too little, whatever it might be. Right? So I'm trying to understand when I look at these things, is it something that's random, right? I can't see any fix to it, any sort of patterning, versus something that's more persistent. This is where we get into that systematic bias. Now, these things can happen, just like with errors, for a variety of reasons. The equations we used in those models we talked about may simplify things in a certain way that do well in the middle of the atmosphere, right? You will hear meteorologists a lot of times talk about how they like things at the 500 millibar or 500 hectopascal level. Things flow a certain way there. Our governing equations are pretty solid right in that range. Yet when it gets to the surface, it's a little more complicated, and maybe our models don't do as good of a job. It might, as I said, have something just to do with the data, whether it's missing data, whether something happened to the quality of the data. This quality control in data is just a huge topic in and of itself. Or maybe we don't have the spatial nature of the data we need to really do a fine-tuned forecast for where you sit or where I sit. Or, as I mentioned, that you got that grid, right? You may have a model that thinks on something on the order of, 25 miles or 25 kilometers or whatever it might be. And you're sitting in the middle of that, and whatever you're experiencing, there's enough variance between those different grid points around the globe that it matters for your forecast. And again, these are just some of the things to think about why it could be going on. Now, like I said, I did a little presentation on this at Georgia Tech during the fall, and I don't think I did a particularly good job on it. I was talking to a little different audience. I was talking to my peers, if you will, and we were talking about how to deal with these biases and the difference between biases and errors when doing the weather competition that you've heard me mention before. So they were thinking about it a little different way, and I was trying to discuss how they might be able to do it on a human level. And we're not going to focus there today, but we'll kind of end with the human component. So we know we have these things, right? Variety of causes, variety of magnitudes. Some of them might be trivial. It may not matter in the grand scheme of things, but sometimes, if your forecast is always wrong by 5 degrees from a certain model, but it's always wrong by 5 degrees in the same direction, it's always too high, let's say, well, then your natural tendency would be, okay, slice 5 degrees off of that and give me my forecast. And that's a little bit about what we're doing, right? But this has been a long part of weather forecasting. People think about the models, but there are people that focus very much on this correction element. That's a lot of what I've done in my career, has been focused on taking these model outputs and doing what we call post-processing. Yeah, it's a fancy little name, but the whole idea with post-processing is, and you may think about it, in terms of images again, right? An image gets some post-processing to maybe sharpen it up, make the colors a little more vibrant. But people always talk about photoshopping photos in this day and age. I mean, that's really post-processing. That image was taken, and sometimes the photographer is doing it to say, okay, the way this sensor and this camera takes this picture, my mind doesn't remember the scene that way, right? And they're doing it to try to give you what they think they saw. Other people might be doing because they're trying to sell you a product, and having something look like X when it looks so much better like Y is the thing to do. But fundamentally, in post-processing with weather model output, what we're trying to do is give you a better forecast. Sometimes we succeed, sometimes we don't. Now, most people who have spent any time with weather, getting weather forecast, may have heard the term MOS, all right? Certainly any of my weather geek listeners out there will have heard the term MOS before. And essentially, this is one of those types of post-processing. Now, a lot of what is done in post-processing gets thrown into that term, but it's not always what's going on. So model output statistics, or that's what MOS stands for, model output statistics. Basically what we're trying to do is we're looking at a relationship, a statistical relationship between one variable and another. So like I said, let's say temperature isn't actually forecasted very well at your level, at your location, specifically where you're standing. I may use MOS to relate a different variable to give you that temperature forecast. And you've heard me mention a little bit ago this 500 millibar behavior. And a lot of times us meteorologists will look at, maybe not for tomorrow, but down the road, if we're looking a week out, we may look at the model, which tends to get that level, like I said, pretty well, and say, I see this at this level. That generally translates into something else at the surface. How much does the surface look like that? How much does the surface temperature look like that? And if I see these variances, I'm going to go, that would concern me. So I may create a model that builds temperature forecast based on what it's seeing at the 500 millibar level. Another example I've seen is somebody who says, okay, the level of humidity in the air statistically over time relates to how often it might rain. And it actually is a better forecast for how often it might rain than what the model says. So again, what I'm trying to do is create this relationship between A and B. And you'll hear, and I'm going to put a link in the show notes where if you really like this topic, you can go and just dig into it. There's tons of material to dig into, and it can be a big rabbit hole or a squirrel. But if you really like the things, there are some quick links that you can go to get a better understanding. But again, the whole idea of that statistical relationship is I'm taking something and I'm predicting something else. We predictors and predictands is what we call them. So the predictors are what the model is spitting out. The predictands are sometimes something the model has also already spit out, but it's perceived that it's not very good. Or it's a variable that maybe the model doesn't forecast, but with the things that the model's giving you, you can work with. Now, a simple way to do this is, like I said, is this relationship between, let's say, humidity and chances of rain at wherever I am at point. And if you plot a bunch of things over time, you would say, well, the model said relative humidity of 80%, and it rained. And then it said 50% it didn't rain. And you could go and build this thing, and anybody's ever done anything in Excel or any sort of spreadsheet, and you're just building something on the x-axis and something on the y-axis, and you're plotting it. Level of relative humidity to, probability of rain, or did it rain? And so you do all these things, and you build this relationship, and you draw a line through it, right? And that creates some sort of statistical relationship, and we call that linear regression. Now, that's a simple linear regression, and it can grow from there, but that's a basic relationship of if something of X, what's the probability of Y, or where is Y going to fit? And so you build this relationship between two sets of data, right? Predictor and predictand. Sometimes simple, most often not that simple. When I was in Chile, I had a need to build a forecast for Streamflow, right? Chile is very based on snowpack melt. So a lot of the Streamflow season is built on when snow melts in the Andes, how does that translate into Streamflow? And what they were finding is their projections, their existing projections and the methods they had used weren't always giving them the answers that they looked for. So a project I worked on was to look at some of this different data that we have and try to build a better forecasting system. So I had multiple predictors, and this is where we get into multiple linear regression, and it doesn't always have to be a line, right? You can create curved line. It's not always as simplistic. That's what I'm saying. It can get more and more complex. But I came up with about 3 or 4 different predictors that collectively gave a pretty good Streamflow forecast. But again, I wasn't using a dynamical model, and they do exist for what the Streamflow forecast was going to be. And a lot of times the challenge is these dynamical models, they take so long to run. And we've talked about this, the computer power and everything else. Usually statistics are much less of a resource hog. And if they can get you a reasonable outcome, and sometimes a better outcome, because that's our goal with these corrections, then why wouldn't you use it? Not to say it doesn't use up resources, right? It can be pretty intensive too. But the idea is we take what came out and we try to make it better in quick order, right? Sometimes it looks like a line relationship. And I'll give you another way to think about it. And we've talked about this before. Sometimes the models have a hard time at seeing extremes in the season, right? Extreme hot in the summer or extreme cold in the wintertime, because it's not within the history. And that's where all this stuff comes from. All of this, everything we do is based on some sort of our understanding of what's the best and the worst it can be. And so the statistical processing will do that. And it may say, for things that are normal temperature, you get them pretty close. But for these extremes, you don't. And so we may do fitting. And we call this kind of the tails of the distribution, right? These extreme events. And we may do some sort of fitting that says that when things are looking in a certain way, we need to stretch that out and say it could actually be worse or not as bad, whatever it might be. All right. So you could do it in, like I said, lines. You could do it with multiple. And visually in your head, this can all get kind of complex. And it's funny when if you go and do a search on simple linear regression on the internet, it'll show you something that a visualization. But if you try to get to multiple, all of a sudden they get into these weird things and it's not as easy to show you. And part of it's because a lot of these things do get hard to visualize in a plain 2D world. But like I said, sometimes you have these one-to-one relationships. Sometimes you're looking at a spatial relationship. We have something we call empirical orthogonal function. Okay, we call them EOFs for short. Makes sense, doesn't it? But this may be looking at patterns and say, okay, get back to that 500 millibar level, and I say, I see certain patterns in this, and if I break down what I'm seeing into multiple patterns that make up that shape, all right, different harmonics if you're in that world. But it's not just for one point I'm looking at as a group. It may tell me something about, what the weather is going to be like down the road. So it can be very simple, very complex, right? But just know in the end, fundamentally, it's still, generally speaking, quicker, faster, cheaper to do than trying to, one, correct a model which can't be corrected to solve the problem, or two, make the model so complex that it takes so long to run that it's not beneficial. So what are we trying to do in the end, right? We're trying to create an objective system, and this is key, right? We're trying to put something together that objectively looks at what we're trying to forecast and says, you did good, but you can do better, right? This is particularly good for when I'm looking at a local forecast, not just a big grid over the planet. Interestingly enough, it helps with the probability. So it's a way, even if I have a single deterministic forecast, and you've heard me talk about endlessly how important probabilities are. You can actually create probabilities with this method of correction or this sort of technique. And all those things can come together, again, very quick, very fast. Doesn't have to be complex. One of the first systems that I put into place when I was doing some coding on this kind of stuff looked literally last couple weeks of temperature forecast. And it looked for, is the model saying it's going to be warm too often or cold too often? Adjust accordingly. It's really that simple. Now, it's not always that simple when you're going out and coding it because, you're looking at different things like what's the forecast lead time, what's the individual station. Now, how do you make all this work? Now, probably the most fundamental thing to making all this work is you've got to have a good history, right? Because essentially what you do is you say, well, the model said X before and it was Y. So what this requires is you to go back in time and see what it's done previously. Like I said, this one that I talked about was just a couple weeks. And it worked pretty well. Was it end all be all? No, but it worked pretty well. And this gets into the seasonality of models and all those things that, during the winter it behaves a certain way. During the summer it might behave a different way. By just looking at the past couple of weeks, I got rid of this possibility that other seasons were overly influencing the prediction. But was it as good as it could be? No. It was a first step. But it was useful. Right? It was better than what the model was telling me. So it achieved that goal of correcting things. But some of the things you just heard me say are part of what can go wrong, right? Or why it is difficult. First and foremost, it's based on this history, right? That history of data. So you got to have good data. If you're trying to create a forecast for a location and you're trying to base it on what happened in the past, your actual understanding of that location has got to be pretty spot on. So if I don't have good measurements, let's say I was trying to do a forecast literally for where I'm sitting, and I don't have good historical measurements, then whatever I'm going to create is going to fail. So there's got to be enough of a history there, right? You got to be careful when you're creating these relationships that you don't overthink them. So you heard me mention that model where temperature, right? Pretty quick. In, out. It's a pretty simple thing. That might be too simple. Maybe I could do better with adding some more components. Maybe I looked at having multiple predictors. But you can also run too far on the other extreme. So you build this model that may work, but you may find, you switch seasons and it doesn't behave. Or cloudy days are different than sunny days, right? So there are all these complexities that the more complex you make it, the better it might be. But then you might get into something that takes so much time to run that it adds no value. And then one of the other things that we run into, not only does data, do we have a good history, but models change. And one of the challenges is for this to work, you've got to have that relationship. I need historical realities to make it work, and I need model history to make it work. So if they change a model and it's significant, it can throw this whole thing off as well. So a lot of times when they do a new version of the model, they'll rerun the past more or less, to give a basis for making these type of corrections. So as you can see, there's an opportunity to improve the forecast, and a lot of this stuff does go on. A lot of the things you look at when you see a final forecast have gone through some sort of correction like this. But for all the benefits that you can get to, there's also these challenges, and it's not just as simple as turning something on and say, okay, I'll revisit you in 100 years. Models change. Data's good or bad. If I'm trying to do something on the past 14 days and there's a problem with the sensor that's measuring the temperature which I'm trying to predict, whammo, that can create real problems. And you got to be aware of that. Because even if it was only down for a short period of time, if that day was off drastically for some reason, that can impact your whole methodology for trying to do a correction. I know. See, I could go on for days and days about this, but, we're at a time when we should probably call it enough. The idea fundamentally in the end is weather data that comes out of the models is good, but in a lot of cases it can be made better. And these MOS or post-processing techniques are a basis for doing that. Theoretically, what we're trying to do is leverage the data we do have and these relationships that we can see to quickly enhance or improve a forecast. However, it's not trivial, and it does have to be revised. So whatever worked for this edition of Model X may not work for Model X.1, right? I don't know. Food for thought. Hope you've enjoyed that. Fundamentally, in the end, it's all about giving the best forecast possible. And it's just a reminder that there are a lot of steps going on and trying to get there. Now, next time we're going to be talking about you getting the forecast. And I didn't get into the human idea of correction. But we do, as meteorologists, when we look at a forecast, think about these same sort of things, right? Because we may even see a bias in the post-corrected things. Or we may know certain situations where the models tend to fail. Maybe it doesn't always fail. And we'll get into that when we get into actually you getting the forecast in your hand. So we'll talk a little bit more about the human component, because it's definitely there. Most definitely. All right, let's wrap up. Came across the stuff with my squirrel yesterday about how snow behaves. You've heard me mention before, one of the things I really like about a fresh snow is how it dampens sound. But what you may not know is that if snow melts and freezes and becomes more ice-like in its behavior, it can actually amplify sound. Snow has some interesting characteristics, and I'm putting a link in the show notes to where you can go and you can investigate kind of the behaviors of snow, the characteristics of snow. Why do people build igloos? Is it really a good insulator? Yeah, actually it can be. It's kind of a neat thing. Snow's pretty impressive. Maybe it's one of the reasons I like it. All right. Let me say, as always, for those that are supporting the forecast, for those of you supporting the podcast, thank you. From Patreon to sharing to taking the survey. It all matters, and it's all appreciated. What is it about the weather.com/support to learn more about doing that? And again, on the survey, what is it about the weather.com/survey, where we're exploring, all right, that translation between weather and what we focus on here in this podcast, weather and being able to respond specifically. How do we help you do that better? Some of the things that we've been touching on this fall. We'll get into another weather in history. What did weather change history next week? I'm going to try to hit some seasonal things. I don't always do that, but this time of year I really do like talking about, I don't know, we won't necessarily focus on winter weather, but we will focus on the role weather plays in some things that are maybe more common in the wintertime. But I don't want to make it too much about that. I want the topic, as always, to translate to wherever you're around the globe. So I'm trying to make sure we do that. But until next time, as we like to say here, just keep in mind, there's much more to weather than the weather itself.
This is 2 White Super Production. We're tired of hearing our uncle grovel, so please support him on patreon.com/weather.